Chapter 20, Set A. A town has 30,000 registered voters, of whom 12,000 are Democrats. A survey organization is about to take a random sample of 1,000 registered voters. A box model is used to work out the expected value and the SE for the percentage of Democrats in the sample. Match each phrase on the list A with a phrase or a number on list B. The items on list B may be used more than once or not at all. So the population in this case would be I would say the population would be 30,000, right? So okay. So the population is everybody in the box. I don't know why they said that as opposed to just 30,000. Population percentage. So what is 12 divided by 30? 0.4. So the population percentage of Democrats would be 40%. The sample would be 1,000. Oh, the sample, the draws, which there are 1,000 draws. The sample size is 1,000. The sample number is going to be, sample is draws, right? And sample size is 1,000. So sample number would be the number of ones you get when you draw. And the sample percentage is the percentage of ones of the draws, and the denominator for the sample percentage is 1,000. Okay. Number 2, a university has 25,000 students, of whom 10,000 are older than 25. The registrar draws a simple random sample of 400 students. Find the expected value in SE for the number of students in the sample who are older than 25. So I'm going to simplify this box. If you were to simplify it, what would you put? 10 ones, right? Nope. 10 ones and 15 zeros. There are 25,000 students, and 10,000 of them are over 25. So we could put 10,000 ones and 15,000 zeros. There are 25,000 total, and 10,000 of them are ones. Yeah, we did 25 minus 10. Or you could say 2 and 3, 2 ones and 3 zeros, right? 2 ones and 3 zeros. We could divide each of those by 5. There are a lot of different boxes we could use. Okay. We want the expected value for 400 draws. So what is the average of the box? So it's, you just add up all the tickets in the box and you divide by the number of tickets. 10 divided by 25. Because there are 10 ones and 15 zeros. So we add them all together and I get 10. And there are 25 tickets total, which is 0.4. Now, is there an easier box than this? Yeah. 5 and, or not 5, sorry. 2 ones and 3 zeros. Or I could just use percentages. 2 out of 5 is 0.4 ones and 0.6 zeros. Why might I want to do that? The average of the box is just 0.4. It's easier to see. No matter which box you choose, the average of the box will always be 0.4. But if the box is written in percentages, then it's just the percentage, 0.4. because that's a 1-0 box. It's going to be 0.4 times 1 plus 0.6 times 0. So the average is just 0.4. Okay. So now I need the expected value. I'm going to multiply this by 400. And I get 160. That's my expected value. Okay. Now I need to find the standard error. So the SD of the box can be found by doing 1 minus 0 times the square root of 10 over 25 times 15 over 25. But there's an easier way than that. It's just this times this. So the square root of 0.4 times 0.6, which is why we like the box to be in percentages. It just makes everything easier. So the square root of 0.4 times 0.6 is an SD of 0.4898. And I need to multiply that by the square root of 400, so times by 20, and I get 160 plus or minus 9.79. That answers A. Okay. Find, oh, sorry. So when we draw from this box 400 times, we expect 160 of the people to be over 25, give or take 10 people. So if you look at the poster, SD or SE of the number is the SD of the box times the number of draws, the square root of the number of draws. Okay, letter B. Find the expected value in SE for the percentage of students in the sample who are older than 25. So how does percentage differ from number? I just divide the SE by the number of draws, so I'm going to divide this by 400. And I get 2.4%. So I expect to get 160 kids, give or take 2.4%. So that's the answer to C. The percentage of students in the sample who are over 25 will be around 160, give or take 2.4% or so. Okay. Number 3, a coin will be tossed 10,000 times. Match the SE with the formula. One formula will be left over. So the SE for the percentage of heads is going to be the SD of the box, which is 0.5, times the square root. Let me write it out. So what's in this box? 0.5 ones and 0.5 zeros, right? And for all coin flipping, the average of the box is 0.5, and the SD of the box is also 0.5. So the SE for 10,000 draws is going to be 0.5 times the square root of 10,000 draws, which is 100, and the square root, so the square root of 10,000 is 100. 0.5 times 100 is 50. So the SE for the number is going to be, or is 50, sorry. And the SE of the percentage is 50 divided by 10,000. Oh, times 100, yeah. So the percentage of heads is just going to be, the SE for the percentage of heads is the middle one, 50 divided by 10,000 times 100. And the SE for the number of heads is 0.5 times the square root of 10,000, so it's the last one. Although the first and last one are actually the same. That's really weird. But Yeah, it's not the first one because it's not actually 50%. The SE is 0.5. The SE is not a, or the SD is not a percentage. The SD is it's a distance, average distance. Yeah, they're the same thing, but the SD is not a percentage. Okay, 4. 500 draws are made at random with replacement from the box 0001. True or false and explain. Now, do we have to make replacements? If the box is really small, yes. If the box is really big, then no. Is this box really big? No, it's very small, so we have to put them back in. But as long as the number of draws is very small in comparison to the size of the box, it doesn't matter whether we put the people back in or not. Okay? A, the number of ones among the draws is exactly equal to the sum of the draws. The number of ones among the draws is equal to the sum of the draws. True. Why is that? Because the other one is 0. So if we end up with 8 after 15 draws, how many ones did we get? 8, and the rest were zeros. Okay, so that's only true in the 0, 1 box. B, the expected value for the percentage of ones among the draws is exactly equal to 25%. True. Yep. Number 5, the box 0012 has an average of 0.6 and an SD of 0.8. True or false? The SE for the percentage of ones in 400 draws can be as follows. So, can we use the box listed to calculate the percentage of ones? No, we have to change it. How do we change this to represent just ones? 4 zeros and 1 1. Because we don't want to add up the draws, we just want to count the ones. So a 2 gives us a score of 0. So we just add the 2 to the zeros. Okay? Or we could say 0.8 zeros and 0.2 ones. That's a better box to use, right? That one makes our life a little bit easier. So, so would we take the square root of 100 times 0.8 equals 16? So the square root of 400 times 0.8 equals 16. No, we would take the square root of 400 times the SD of the new box. So the new box is the square root of 0.8 times the square root of 0.2. Or sorry. We need the new SD. We changed the box. So it would be the square root of 0.8 times 0.2. Okay. And then when we multiply that by 20, so that's wrong. And then the SE percentage of ones would be 16 over 400, which is wrong because that 16 is wrong. Right? They used the wrong box. If you're counting up the number of ones, you don't use the regular box. Is that it? Oh no, we got lots more. Number 6. 900 draws are made at random with replacement from a box which has 1 red marble and 9 blue marbles. The SE for the percentage of red marbles in the sample is 1%. A sample percentage which is 1 SE above is expected value equals. So what's in the box? 1 1 and 9 zeros. Or we could say 0.1 1, 10% of them are ones, and 90% of them are zeros. Either way it will work, but the bottom boxes makes things a little more simple. Okay, so we want the SE for the percentage of red marbles drawing 900. So we don't need the average in this case. We're just looking for the SE of the percentage. So we're going to take the square root of 0.1 times 0.9. That'll give me the SD. Square root of 0.1 times 0.9. And I get 0.3. What does that mean? That's the SD. The number in the box, the numbers in the box on average are 0.3 units away from 0.1. Okay. Now to find the SE for the number, I multiply this by the square root of the number of draws. So 0.3 times 30 is 9. So my expected value is 10%, give or take 9. But I want a percentage there. So I take that 9 and divide it by the original 900 draws. So the answer is 10% plus or minus 1%. Okay. How do I know the expected value is 10%? That's the average of the box. So we expect 10% of the draws to be within, or sorry, we expect 10% of the draws to be red, give or take 1%. All right. Number 7. Someone plays a dice game 100 times. On each play, he rolls a pair of dice and then advances his token along the line by a number of squares equal to the number of total spots thrown. About how far does he move, give or take how much? Okay, you're rolling a pair of dice. What could happen when you roll dice? 2 dice. Anything from 2 up to 12. Okay, but how many different ways are there to roll 2 dice? You could get, how many ways are there to get a 2? 1 way. 1, 1. How many ways could you get a 3? 2 ways. A 1, 2 or 2, 1. There are 36 total, right? If we draw that array, and we do 1 through 6 here and 1 through 6 here, then we'll have 1 way to do that, 2 ways to do that, 3, 4, 5, I kind of messed that up, 6, 5, 4, 3, 2, 1. And that adds up to 36, right? So in the box, this is the 2, 3, 4, 5, 6, 7, 6, 5, 4, 3, 2. There's 1, oh wait, that's not right. 6, sorry. 8, 9, 10, 11, and 12. So there's 1 2 in the box, and 2 3s in the box, and 3 4s, and 4 5s, and 5 6s, and 6 7s, and so on. So the question asks, someone plays a dice game 100 times. On each play, he rolls a pair of dice and then advances his token along the line by a number of squares equal to the numbers thrown. About how far does he move, give or take how much? Okay. Well, we know that the box has a 2, 2 3s, 3 4s, 5 5, 5, 5, 6 6, 6 6 6, 7 7, 7 7, and so on. There are 36 numbers in the box. About how far is he going to move in 100 draws? Well, what's the average of the box? It's going to be exactly 7, right? Because there are just as many 2s as there are 12s, and so those cancel. And there are just as many 3s as there are 11s, and those cancel. So we know that the average of the box is 7. Okay. If we make 100 draws, we times that by 100, So we would expect to move 700 spaces. Give or take how much? Well, I would need the SD of the box. Um, so I think we're going to have to plug that into our calculators. Okay, watch me as I type these in. So stat, edit. So 2, 3, 3, 4, 4, 4, 5, 5, 5, 5. Oops. How many fives do I need? 4? So 1, 2, 3, 4, 5. And now 1, 2, 3, 4, 5, 6. And then 1, 2, 3, 4, 5. And then 1, 2, 3, 4. And then 1, 2, 3. And 1, 2. Oops. And then a 12. So stats, calc, one variable stats. And we get an SD of 2.4. What do I do with that? Multiply that by 20. So 2.4 times 20. 48. So does it want the percentage? Probably. Let's find the percentage. 48 divided by 400 draws. Uh, did I mess that up? Oh, we're doing 100 draws. Sorry. It's 2.4 times 10, not 20. So I just used the wrong number of draws. Okay? Right. So 700 plus or minus 24. All right. According to Sherlock Holmes, when the individual man is an insoluble puzzle, in the aggregate he becomes a mathematical certainty. You can, for example, never foretell what any one man will be up to, but you can say with precision what an average number will be up to. Individuals vary, but percentages remain constant, so says the statistician. The statistician doesn't quite say that. What is Sherlock Holmes forgetting? Chance error. He is overlooking chance error. Good old Sherlock.